In September 2023, James Webb Space Telescope looked at Europa, Jupiter's ice-covered moon, the one scientists have spent 40 years calling the most promising place to search for life beyond Earth. What Webb found was not life. What it found was carbon dioxide, concentrated in a specific region of Europa's surface, with an isotopic signature pointing to a single origin, the ocean beneath the ice. Not delivered by comets, not from space, from inside. That detail, carbon from a subsurface ocean making its way to the surface, sounds like good news if you're looking for habitable chemistry. And it is. The problem is everything else Webb confirmed about Europa in the same observations. The radiation environment that makes the surface lethal in minutes. The chaotic terrain where the ice shell is being torn apart and refrozen in cycles that would shred any structure placed on it. The ocean that contains more water than all of Earth's combined, sitting under conditions that have no parallel anywhere humans have ever been or sent instruments. Europa Clipper, launched in October 2024, is on its way to the Jupiter system now. It will arrive in 2030 and spend 4 years flying past Europa 49 times. What Webb found in its final detailed observations before Clipper takes over is the baseline against which everything Clipper measures will be compared. And that baseline is more complicated and more extreme than the textbook version of Europa suggested. Europa is the fourth largest of Jupiter's 95 known moons, and the second of the 4 Galilean moons, the ones Galileo discovered in 1610 that proved not everything in the sky orbited Earth. It is slightly smaller than Earth's moon, 3,122 kilometers in diameter, orbiting Jupiter at a distance of about 671,000 kilometers, completing one orbit every 3.5 Earth days. The surface is water ice. Underneath the ice, somewhere between 10 and 30 kilometers down, depending on where you drill, is a global liquid water ocean roughly 100 kilometers deep. More water than all of Earth's oceans combined, kept liquid not by proximity to the sun, but by tidal heating. Europa is locked in an orbital resonance with the moons Io and Ganymede. For every one orbit Europa completes, Io completes 2 and Ganymede completes 1/2. This resonance keeps Europa's orbit slightly elliptical, which means Jupiter's gravity pulls on it with varying force as it moves closer and farther from the planet. That variable pull flexes the moon, generating friction deep inside the rock and ice, releasing heat. The ocean stays liquid. It has been staying liquid for billions of years. The evidence for the ocean is not inferred from a single measurement. It is triangulated from multiple independent datasets spanning 3 decades. The Galileo spacecraft detected a magnetic field at Europa that could only be explained by a saltwater conductor beneath the surface. Seawater conducts electricity, and Europa's ocean, laced with salts leached from the rock below, does the same. The surface shows features, long dark lines called lineae, chaotic terrain blocks that have shifted relative to each other, lenticulae that look like melt-through spots, that are consistent with an ice shell moving over a liquid layer. Hubble detected what appeared to be water vapor plumes erupting from the surface near the South Pole, though those detections remain debated. The ocean is real. What is in it is the question Europa Clipper is being sent to begin answering. What Webb found in 2023 changed what that question looks like. Webb's near-infrared camera detected carbon dioxide on Europa's surface in concentrations and locations that had not been resolved by previous instruments. The CO2 is concentrated primarily in a region called Tara Regio, a large area of chaos terrain in Europa's northern hemisphere, roughly 1,800 kilometers across, where the ice surface is heavily disrupted. Carbon dioxide is not surprising on an icy moon in the outer solar system. It appears on many bodies. What matters is where it comes from. CO2 on Europa could arrive from outside, delivered by micrometeorite impacts, produced by radiation breaking down organic compounds on the surface, or swept in from Jupiter's magnetosphere. All of these external sources would distribute carbon dioxide more or less uniformly across the surface over time. What Webb found was not uniform distribution. The CO2 is concentrated in Tara Regio, specifically in the chaos terrain, where the ice shell is youngest and where material from the subsurface has most recently been brought to the surface. The carbon isotope ratios in the Webb spectrum are inconsistent with external delivery and consistent with a carbon source that has been cycling through liquid water chemistry. The ocean contains carbon. That carbon is making its way to the surface through the same processes that create the chaos terrain: upwelling of warm ice, partial melting, refreezing. This is significant for habitability because carbon is one of the essential elements for the chemistry of life as we know it. An ocean with carbon, liquid water, heat from tidal forces, and salts from rock. That combination covers the basic requirements for the kind of chemistry that, on Earth, led to living cells. The Webb CO2 detection does not mean there is life in Europa's ocean. It means the ocean has the carbon inventory to support the kind of chemistry that could, in principle, produce life. That is a different and more precise statement than anything that could be said before September 2023. Jupiter's magnetosphere is the largest structure in the solar system after the Sun's own magnetic bubble. It extends 75 million kilometers toward the Sun and stretches over 700 million kilometers in the opposite direction, past the orbit of Saturn. Inside this magnetosphere, Jupiter's powerful magnetic field traps charged particles, electrons and protons, and accelerates them to near-relativistic speeds. Europa orbits inside the most intense part of this radiation environment. The particle flux at Europa's surface is approximately 540 rem per day. A lethal radiation dose for a human is generally considered to be around 400 rem received over a short period. A person standing on Europa's surface in a standard spacesuit, the kind used on the International Space Station, would receive a lethal dose in less than 1 day. Without any shielding, the exposure is measured in hours. This is not a colonization obstacle that better suits or more radiation-hardened materials can easily solve. The particle energies involved are high enough to penetrate significant shielding. The electrons trapped in Jupiter's radiation belts reach energies of tens of mega-electron volts, comparable to medical radiation therapy beams. Any surface structure on Europa would need to be buried under several meters of ice or rock to achieve survivable conditions, which creates its own engineering challenges given the dynamic ice shell. The radiation does something else that Webb's observations help characterize. High-energy particles bombarding the surface ice break apart water molecules and recombine them into oxidants, hydrogen peroxide, sulfuric acid, and other reactive compounds. These oxidants accumulate on the surface. If the ice shell is cycling material between the surface and the ocean, which the chaos terrain and CO2 findings suggest it is, then oxidants are being delivered to the ocean along with that carbon. On Earth, the combination of reductants from hydrothermal vents and oxidants from the surface drives metabolic chemistry that supports entire ecosystems without sunlight. Europa's ocean may have the same setup, at planetary scale, powered by Jupiter's radiation rather than sunlight. Tara Regio, where Webb found the CO2, is chaos terrain. On Europa, chaos terrain is not a metaphor. It is a specific geological classification for regions where the surface ice has broken into blocks, shifted, rotated, and refrozen in a jumbled configuration that no longer resembles the surrounding smooth plains. The blocks look, from orbit, like ice flows on a partially frozen Arctic Sea, locked in place after the underlying slush refroze. The mechanism that creates chaos terrain is debated, but the leading models involve partial melting of the ice shell from below, pockets of warm, possibly liquid water rising toward the surface, destabilizing the overlying ice, and then refreezing as the warm material dissipates. This process brings subsurface material to the surface, which is why the CO2 concentrates in Tara Regio rather than in the smoother, older terrain nearby. The chaos regions are the places where the ocean and the surface are most recently connected. Webb's infrared imaging resolved compositional differences across Europa's surface at a level no previous telescope could achieve. The concentration of CO2 in Tara Regio versus its absence in the surrounding terrain is a direct measurement of how heterogeneous the exchange between ocean and surface is. It is not a slow, uniform process of gradual diffusion. It is patchy, concentrated in specific active regions, driven by localized dynamics in the ice shell. This has implications for where Europa Clipper should concentrate its closest passes. The chaos terrain is where the most recent ocean surface exchange happened. Flying low over Tara Regio and similar regions, sampling any plume activity, measuring the surface chemistry in detail, mapping the subsurface structure with radar, gives Clipper the best chance of characterizing what the ocean is actually contributing to the surface, and vice versa. It also means the ice shell is not a passive barrier. It is active. It is cycling. The same processes that make Europa scientifically compelling, the connection between ocean and surface, the upwelling of warm material, are the processes that make the surface geologically violent. Nothing stays in place. The lineae that cross Europa's surface, some of them extending thousands of kilometers, are cracks produced by the constantly shifting tidal stress. They open, close, fill with fresh ice from below, and open again on timescales of years to centuries. Europa is not a place where you put a colony on the surface and drill down to the ocean. The radiation eliminates that option. The dynamic ice eliminates it further. The tidal stress that creates the lineae and chaos terrain is ongoing. Any structure anchored to the ice would experience the same forces that crack the surface, and no engineering specification for a permanent surface habitat on a body with this radiation flux and this ice dynamics currently exists. The realistic path to Europa is orbital and flyby, which is exactly what Clipper is doing. 49 close passes over 4 years, each one spending only a limited time in the intense radiation environment before pulling back out. The spacecraft's electronics are shielded in a titanium vault. Even so, the radiation will degrade them over the mission's life. The plan is to accomplish as much science as possible before the hardware fails. For any long-term human presence in the Jupiter system, the operational base would almost certainly be at Callisto, the outermost Galilean moon, orbiting outside the worst of Jupiter's radiation belts. Callisto receives roughly 0.01 rem per day, a radiation environment manageable with moderate shielding. A base at Callisto could support crewed missions to Europa orbit using robotic spacecraft, maintaining the scientific investigation without exposing crew to the radiation environment directly. The deeper significance of Europa for survival planning is what it tells us about where life might exist in the universe. If the combination of liquid water, carbon chemistry, tidal heating, and oxidant delivery from radiation is sufficient to support life, and Europa is the nearest test case for that hypothesis, then the same combination exists on Enceladus, on Ganymede, probably on Titan's subsurface, and on hundreds of icy moons around exoplanets in other solar systems. The question of whether life requires a star, requires sunlight, requires surface conditions, is being tested at Europa. The answer changes how we map habitability across the galaxy. The horrifying part is not the radiation, or the chaos terrain, or the ice dynamics. Those are engineering problems. The genuinely unsettling part is the ocean itself, 100 kilometers deep, in total darkness, never touched by sunlight, heated from below by tidal friction, with an active chemical cycle that has been running for billions of years. Whatever is or is not in that ocean has had more time and more energy and more liquid water than the environment that produced the first life on Earth. We are about to start finding out what that means. The ice shell thickness is one of the most consequential unknowns. Models range from 3 kilometers, thin enough that chaos terrain involves direct communication with liquid water, to 30 kilometers, in which case the chaos formation process involves only partially melted ice with no liquid phase reaching the surface. The distinction matters enormously for what kinds of chemistry are being exchanged and what Clipper's radar sounder will see when it maps the subsurface. The plume question is unresolved. Hubble detected what appeared to be water vapor erupting from Europa's surface near the South Pole in 2012 and again in 2016, at heights of 200 kilometers. Subsequent attempts to confirm the detections were inconclusive. Some searches found nothing, others found marginal signals. If Europa has active plumes like Enceladus, Clipper can fly through them and sample the ocean directly, without drilling through the ice. If it does not, sampling the ocean requires either landing and drilling or inferring ocean composition from what reaches the surface through the ice exchange processes. The plume question will be one of the first things Clipper addresses. The salinity and chemistry of the ocean are unknown. The magnetic field induction measurement from Galileo confirms the ocean is electrically conductive, salt water, but does not constrain the specific salt composition. Is it a sodium chloride ocean like Earth's? A magnesium sulfate ocean? Something more exotic? The salt composition affects everything from the freezing point of the ocean to what chemical reactions are thermodynamically favorable inside it. And the hydrothermal question. Does Europa have active venting on the ocean floor, where hot rock meets water and drives the kind of chemistry that supports deep-sea ecosystems on Earth? Tidal heating suggests the rocky interior is warm enough for some hydrothermal activity, but whether that activity produces the concentrated chemical gradients needed to drive metabolism is unknown. Clipper's gravity measurements will help constrain the interior structure. The rest requires something that Clipper is not equipped to do: going under the ice. Webb looked at Europa and found carbon from an ocean that has been running for billions of years, in a radiation environment that kills without warning, on a surface that cracks and reforms and cycles material in and out of depths we cannot reach. Europa Clipper is on its way. It will arrive in 2030, make 49 passes, and send back more data on Europa in 4 years than has been collected in the previous 4 decades. What it finds will either confirm that Europa's ocean is chemically rich enough to support life, or it will reveal what is missing. What ingredient or energy source or process is absent that makes the difference between chemistry and biology? Either answer is significant. If the ocean supports life, it will be the most important discovery in human history. If it does not, despite having water, carbon, heat, and time in quantities that exceed what Earth had when life first appeared, then something about the conditions for life is more specific than we understood, and the universe becomes a lonelier place. Webb saw Europa. What it found is complicated and extreme, and not what the simplified version of this story usually includes. The ocean is real. The carbon is real. The radiation is real. The chaos is real. Clipper will tell us what is in the dark below all of it.